So, second speaker this morning, it's a pleasure to welcome Nick Hill from Glasgow University, and Nick will be telling us about modelling the pulmonary circulation. Nick.
Thank you. So, first thing to say is that this is obviously joint work with various colleagues. Gareth Vaughan is a former PhD student of mine at Glasgow University, as is Umar Qureshi, who is now a postdoc with Mette Olofsson at North Carolina State. And Charlie Peskin was very helpful with many aspects of this work, and these are two of my clinical colleagues, and I'm particularly working on now with the Scottish Pulmonary Vascular Unit to look at more patient-specific models as well, which I'll tell you about in a little while. So why am I interested in modelling the circulation, and in particular the pulmonary circulation? How does it relate to the themes of the workshop here? Well, the key thing is that the circulation provides an environment in which the cells and tissue level modelling takes place, and many of it is quite dynamic. So if you're looking at tissue in the wall of the heart, in the walls of the arteries, or in the lungs, the fact that you've got a pressure pulse going through, you've got a dynamic environment, changes the way that the remodelling takes place within the system. So it's important to understand this if you're going to build models that are multiscale, in the sense that you get interactions both ways, from the small scale to the large, and vice versa. And I should have added that Gareth was funded by the EPSRC and Umar by the Pakistani Higher Education Commission. So the cardiovascular system, it's got two main components: the systemic circulation, which is the flow of blood to everything except the lungs, and then the pulmonary circulation. And these are separate because the way that the heart works, it's got two pumps. It's got a left and right to the heart, and left and right ventricles that provide the power for pushing blood flow through the system, as this cartoon illustrates. The systemic arteries are a high pressure system. The left ventricle generates pressures that are 5 times greater than those in the pulmonary circulation in normal healthy state, and has a range of vessels. In particular, these arteries are muscular, and the smaller arteries, some of them called the resistance arteries, from perhaps about 500 microns in radius down, they actively control the pressure in the system, and the main pressure drop occurs in the systemic circulation across these. The pulmonary vasculature is different. The vessels are less stiff, and there's no real equivalent of the resistance arteries. The other big difference is that in the systemic system, the pressure drops right off as you go down to the capillary bed, and then the venous return is low pressure. And as I'm sure many of you know, there are valves in your legs, for example, that help with the return of the blood back to the heart, and just my walking around at the moment helps to pump blood back to the heart, ready to go around the pulmonary circulation. So that's a low pressure system that I'm not going to model. It's a rather different system. The pulmonary circulation is different. There's a pressure pulse that persists all the way across, through around the alveoli, through the small blood vessels, and back to the left atrium of the heart, ready to be pumped out to the systemic circulation. So it's a different system. It's a pressurized venous system. So I'm going to tell you a little bit about the systemic artery model. This is not my work. This is Mette Olofsson's work initially. So she, for her PhD thesis in 2000, published this work. And the cartoon illustrates quite well what one's doing to achieve a mathematical model and computational model that you can run quickly. When I say quickly, I've got a standard workstation on my desk, and I can run a code for working the circulation in systemic or the pulmonary circulation within, I don't know, half a minute, times like that. So it's a fast code. And the way this is achieved, even though you've got something like, well over 10 to the 8 vessels in this, is first of all not to try and compute detailed 3D flows in all the vessels. That's just far too complicated and far too difficult. Even today, people can only really achieve that for a very minimal number of vessels and a bifurcation or two. What we are going to do is take a 1D cross-sectional average of the flow. So that gives me one spatial direction. This is flow along the vessels and time, of course. So it's a 1D cross-sectional average, and that achieves a lot of the reduction in complication that's needed to be able to compute these things quickly. In the large systemic arteries, this is a wave problem. We treat blood as being an incompressible fluid, which is fine on the scales at which we're working. So the way that you get a finite propagation velocity is that all the vessels, large and small that our model, are compliant, they're elastic. And so the wave propagation is the change in area of this vessel as the wave propagates down. So we'll use a common Lax-Wendroff scheme, or any other scheme you like, to compute the propagation of the waves down the vessels and the reflections back from bifurcations. And then we have to do something for the very many small vessels in what I shall call vascular beds, which are indicated here, corresponding to major organs and so on. And we'll do this using a structured tree. So most of this I've said. Yes, in the large vessels, you assume a flat velocity profile with a boundary layer. These are solved numerically, of course. And the trick with the smaller arteries is that we think they're small enough that you can linearize the Navier-Stokes equations that apply, and that allows you to do some mathematical analysis. And then these return a boundary condition that you can use to calculate your flows properly through the system. The algorithms are fast and recursive, and then what I did later was also to help to produce a new algorithm so we could calculate pressure and flow within the structured trees as well, the vascular beds, which is relevant for tissue modeling and so on. How was the code started? Well, it was started from MRI measurements of flow. So this is flow coming out of the left ventricle, out of the heart. So that's in units of centimeters cubed per second, as you can see, and that's over 3 periods. And what you have to do in these models, of course, is to conserve flow. So every time flow comes down a parent and divides into 2 daughters, D1 and D2, then you have to make sure that the total flow is conserved as you go into the daughters. And in a 1D model, you want continuous pressure at the bifurcation. So the pressures there are all the same. We model the large arteries in terms of their areas, and these can be tapered. I don't think there's much more to say on that cartoon. And so these are the flow equations for the large arteries once you've done the averaging across the cross-section. So this is the volume flux averaged across the cross-section, and A is the cross-sectional area. So this is a standard continuity equation, allowing for the fact that the area is changing as the flow goes down. The momentum equation comes from the Navier-Stokes equations, again allowing for change in area. You'll recognize the nonlinear term there, the pressure gradient, and this resistance term comes from assuming that you have a boundary layer and integrating across that. So it does involve the viscosity nu here, but that's where that term comes from. And then to connect these, you need some sort of tube law or state equation that connects the pressure to the cross-sectional area. This is a very simple law here in terms of Young's modulus E, quick measure of the elasticity, the thickness of the wall, H, and the resting radius, R0, which corresponds to the area, A0, of course. And P0 is an external pressure. So in the vascular beds for the structured tree, what you do is for every parent, you divide it into 2 daughters, and the radius of one daughter is alpha times the radius of the parent, and the radius of the other is beta times that, where alpha and beta are numbers between 0 and 1, and typically alpha will be about 0.9 and beta will be about 0.6. And we get that from data on vascular beds. It doesn't have to be the same for each vascular bed, and of course it's some sort of average to what's going on. And these vessels are elastic too, and I've already said they provide the boundary condition onto the large arteries. Within the structured tree, you can linearize the equations, then you take Fourier series in time because we're assuming it's periodic. where omega here now is the frequency and the large letters denote the Fourier transform quantities. So the momentum equation reduces to this because it's linearized. These involve Bessel's functions because you're doing flows in tubes. And this is what's happened to the continuity equation, and C here is a compliance, elastic compliance of the wall. And to explain briefly how this algorithm works, you can solve those simple equations. It gives you the flow in frequency space and the pressure in frequency space, and then you're interested in calculating the impedance, which is the frequency-dependent resistance. It's important that it's frequency-dependent. It's not one steady-state resistance. And it involves the wave propagation velocity little c here as well. So this is a solution. Here are your arbitrary coefficients. You'll note, of course, that actually this is only a function of a over b, the ratio of a to b, not a and b separately. And what this means is that if I know the impedance at the far end, the distal end of a vessel, so this is x equals L, I can, from that formula, work out what it is upstream. And I can keep working upstream from daughters to parent using the bifurcation condition, which just comes from the rules I just mentioned for conserving flow and having constant pressure. And so if you know at the smallest end of your vessels what your impedance is, in fact we'll set it to be 0 at some minimum radius, you can work your way up the tree to work out the total impedance, the frequency-dependent impedance of your vascular bed. So that's what Meta-Olesen did very successfully, and she presented results for flow and pressure, but this is flow at various sites along the arterial tree. This is the aortic arch. As it happens, the dashed lines are the measured MRI results and the solid lines are the simulations. You'd expect very good agreement near the aortic arch because that's where you had your input. That was your initial condition. But as you move further downstream, then you're computing these flows. And really the agreement was pretty impressive at that time. It's getting a lot of the features right. And what I'd like to emphasize is, well, I'll come to that in a little while. So here are some pressure results for the systemic arteries, and this is working it down into a vascular bed. So these were some of the new results that we did, and I'm going to show you what happens as you go down successive generations. So I should be clear that this is the time for one heartbeat. I think the period here is about 0.7, a fairly fast heartbeat, and this is the pressure in millimeters of mercury. I'm sorry, but these are the units the clinicians use all the time, but you can multiply by 133.3 to get it into pascals. Now, just see if this works. So this looks like something time dependent, but what I'm actually doing is showing you what happens as you go down successive generations in the tree, and this is a summary of all of those. And the thing I would point out is that you're getting the peak of the pressure wave occurring later in the cycle as you move down the tree. You can see its propagation. You can see some peaking of this. This is a well-known nonlinear effect. And then the pressure becomes steadier as you move down through the generations. Okay? It depends quite a lot on one of our parameters, which is the length to radius ratio, which is one of the geometric parameters you'd measure for a vascular bed, but it doesn't depend strongly on the number of generations. Now, here's some clinical data by Levy in 2001, looking at a summary of various people's measurements. It's a review paper of looking at intravascular pressure, again in millimeters of mercury, against the log of the diameter of vessels in microns. And the key feature is that once you get down to around 100 microns, maybe a little before that, you start to get, on this scale, what looks like a linear drop-off in pressure against this log diameter until you get down to the capillaries, the small vessels. And these are the results of averaging pressure against vessel radius from our computation. So this wasn't something we built in. And here I'm showing log of the radius actually in microns and log to the base 10 and the mean pressure. And we're getting also this linear behavior. The wriggles here are really just to do with the binning that you do for averaging across the vessel radius. And the green and blue lines show the extrema. So if this is a vascular tree, then one is going down this branch and one is going down the other branch. But what we're interested in is the average. So we get the same sort of behavior and we're able to estimate how the mean pressure drops off. So that was very reassuring and useful for soft tissue modeling. Well, that was by way of an introduction. More recently, in the last few years, we've been looking at the pulmonary circulation and needing to include both the pulmonary arteries and the pulmonary veins, because as I said, they're pressured. We need to have to understand how to couple structured tree models. We're interested in diagnosis and disease, and to understand the basic mechanics of the pulmonary circulation and its role in remodeling. In itself, it's a remarkable system. Again, as this cartoon illustrates, it branches very, very rapidly, and of course the arterial blood is blue and then it's coming back oxygenated as red into the left atrium. This is a cast of the airways shown in white, and here in blue the pulmonary arteries and in red the pulmonary veins, and you can see how closely the two structures are linked and just how rapidly it divides out. And one measure of that is apparently in the average adult male, when you get down to the smallest scales, the area for blood gas exchange is about 70 meters squared, which is roughly the area of a tennis court. And we're getting down to average capillary radii of something like 4 microns. We have the same sort of structured tree before. In fact, much of the data we had for the systemic circulation came from pulmonary arterial trees because they're the easiest to get. There are various ways of classifying this, but this in particular is a cast showing you how these branch, and this is what we replace it with, the structured tree. So this cartoon shows us how we do the computation. So we have MRI data for the flow out of, this time, the right ventricle into the main pulmonary artery, which divides into left and right pulmonary arteries. They're not of the same length and size because your heart is on the left, and so there's asymmetry built in originally. And then we can model the next 2 generations, though these start to get very patient-specific, so you really need to measure these with MRI data or CT data. And on the ends of each of these, we put vascular beds with many more branches than indicated here. This is just a cartoon to illustrate it. And we've got to join up the arterial vascular beds to the venous vascular beds. So that's the first thing we've got to do, is join all these trees up. And we've finished it up with 4 large vessels, the left inferior vein, left superior vein, and the right veins, all draining into the left atrium. This is a fairly common physiological structure in that the 4 tubes just come straight into the left atrium, but sometimes they merge, and that's another healthy, normal case, and you may just get 2 coming in. And we've kept things very simple here. We haven't modeled the contraction of the left atrium. We have, and even in fact there's a semi-valvular apparatus at the ends of some of these. We've just kept the external pressure steady at 2 millimeters of mercury, so we can figure out what's happening in the pulmonary circulation without the complication of the atrium. So that's what we need to do. And clearly we don't want any loose ends, otherwise we'll lose blood. So we have to match up the trees in a sensible way. There are various parameters I may mention. There are really only 2 parameters, independent parameters out of all these. Either you can work with alpha and beta, these daughter to parent radius radii, or the cross-sectional area, the change in cross-sectional area as you go down the tree, or an exponent here, which I could say more about if we have more time, but I think I should move on. What we do have is the ability to make good measurements of the large pulmonary vessels, as I indicated, and this cartoon is really just to illustrate we've got lengths and diameters at the ends of each bifurcation. So we know this geometry fairly well. And here is some of our data. As our clinical radiologists get more expert, they'll be better at measuring some of these. So most of these we were able to calculate. It was a little harder finding the veins. It's not something that radiologists are used to doing, so sometimes they have to struggle and get out anatomy textbooks to say, well, where should this vessel be, and so on. So not just the mathematicians who struggle sometimes, but it can be done. And it's non-invasive, and for most patients this is quite possible. It's not all patients can go into the MRI scanner, of course. And this, I could have shown you earlier when doing systemic arteries. This is where a lot of the data on branching came from. I'm not expecting you to read all this table. It's quite old data from the 60s, but there are something like 17 generations of vessels in the pulmonary circulation. That's quite typical. And you go down to, in the smallest size, something like 3 times 10 to the 8 vessels. So it's a huge thing. But we do know average diameters and lengths and so on. So we know all of this geometric data. For our work, we had to deduce some properties of the pulmonary circulation, particularly it says physical, but I mean the elastic, the compliance. And in particular, this is data showing the log of the length to the log of the radius of the vessels. And there is a sharp change in gradient as you get down to about 50 microns, which, and these are 2 sections from that. So this is for R less than 50 microns, and the slope here is 0.47, so about a half, whereas here for the rest of the vessels, the slope here is 1.1. And also if you look at the pulmonary veins, again you find the slope here is about 1. So something is happening as you get down to about 50 microns, and because we don't yet have a good model flow around the alveoli, that was our cutoff point. So we took our vessels down to a minimum size of 50 microns and then joined up the trees. We also needed, so that was length to radius ratios. We also needed compliance, and this is fairly standard across a whole range of species here. You can probably see dog, cat, human, rat. Pig, definitely pig should be in there. They're very close to humans, and other favorite animals. Both for the arteries and veins, and so we've got some estimates from measurements of how they dilate against pressure of the compliance of these vessels. Our inflow data. So this is taking an MRI scan. The chap is lying on his back, his head towards you, and this is a section through his chest, and you can see some of the larger arteries. You're picking out the main pulmonary artery, and if you get your cross-section right, you can get flow rates under MRI scans. So we have good quality data, and this is the flow against time for 1 cycle. We also were able to get data for the pulmonary vein return flow. These are the 4 pulmonary veins. They're not all the same shape and size. They've got this very typical so-called biphasic pattern here to them. And then this is probably where the left atrium is contracting. Yes, that's right. And these average to these values, and the good thing is that the flow out pretty much matched the flow in, so we felt we had a good data set and nothing untoward was happening. So with all this data, we can assume the trees are topologically similar and join them together. In principle, the material and geometrical properties are different, and we want a matching condition so that when we do our computations, I can link what's happening in the large arteries with the large veins where I'm doing my wave-like calculations. And the trick is to use the admittance, which is 1 over this frequency-dependent resistance, the impedance. So these were the same linearized equations in the vascular beds. Again, you can work out Q and P, and if I have just one elastic tube here, what I mean by the admittance is I can write the flows Q1 and Q2, convention happened to be that the flows were in on both ends, in terms of the two pressures, and the matrix in the middle is the admittance. And of course there's a special case when there's steady flow, when the frequency is 0, that's just Poisson flow, and the CL and SL here just are shorthand for sines and cosines of terms, so yes, these in particular. And these are scaled, of course. Now the nice thing is if you try and link vessels in parallel, so you've got, remember we're constructing a tree and joining them together, so if you've got this circuit and you link it with this circuit, then the admittances just add. It's not quite so nice when you add them together in series, but you can calculate it. So these are the two admittances joined together. And most importantly, you can write a nice algorithm, a fast recursive algorithm to do this. And for the whole vascular bed, it gives you in Fourier space the admittance matrix linking flows to pressures. And when you do the computation in real space for the wave propagation, this leads to convolution integrals integrated over a whole period. I think the notation is fairly clear. So this will be the pressure on the arterial side, the flow on the arterial side, and then pressures and flows on the venous side. And so in this code and the other code, you need to integrate over 4 or 5 periods, and then everything settles down and converges nicely. So you're using information from the whole of the cycle. The contrast here is to what are called Wind-Kessel models, where people put a fixed resistance and possibly a capacitance and an inductance term, even like an electric circuit on. But these at most give you 3 parameters, and what people have done before is to take, on the systemic side, is to put lots of these on the ends of your computational vessels, tune all the parameters so you get flows that are right, and there are a lot of parameters as you'll realize. But what it can't do is tell you anything about what's happening in the microvasculature, the smaller vessels. It can't, and gives you no rational way to alter things to mirror what might be changing physiological conditions. You can't do that. You can use it for other things, but that's the limitation. And so this is a big advantage if you really want to know what's happening in the circulation. And as I say, it computes quickly. Here are just some illustrated results showing flows and pressures at vessel inlets in blue, and then further down the vessels. So this is the main pulmonary artery. As you'd expect, you can see slight steepening and changing as you move down the vessel, and then changes in pressure as you move into the right pulmonary artery and the left pulmonary artery. The flows don't change much along these vessels on the first vessel, because this is the input anyway to the system, though we can run the model with inputting pressures and so on. As soon as you bifurcate into the first 2 branches, the right and left pulmonary artery, you see the change in flow because the flow has been divided, and you'll see that the changes in geometry mean you get a much larger flow through the left pulmonary artery than the right pulmonary artery for this individual. In terms of the return flow, the straight line at 2 millimeters of mercury is the boundary condition we put on at the end, but further up you can see the biphasic type of flow in all of these return vessels. These are 3 out of the 4 that we're showing here. And you can also see this in the flow too. You can look at the pressure drop across vascular beds in the pulmonary circulation, pretty much as we did in the systemic circulation, so you write an algorithm for that. And so this shows the pressure in millimeters of mercury going from about 20, this is a healthy individual, and here I take log of the radius down to 50 microns, and then I've increased the radius again on the log scale, and you can see that the average is more or less linear here again, and the wiggles are to do with the way we average across the bins rather than anything else. You should pick a straight line there. And so it gives us estimates for how the pressure varies across the system. I can also use this to look at certain types of pulmonary disease, so-called pulmonary hypertension, high pressure in the pulmonary circulation. There are the international clinical classifications give you about 5 groups. One for causes they're not really sure of. One to do with faulty valves on the left side of the heart, which just raise the pressure in the left atrium and through the whole system. I mean, it's serious, but it's a secondary condition of a primary problem. But these are pulmonary hypertension itself. So group 1, pulmonary arterial hypertension, is when the vessels of less than about 500 microns in diameter have increased stiffness and consequently resistance to flow. It's a response to various types of hypoxia. So we've got stiffer small vessels. The second one is where you effectively get a loss of pulmonary vessels. So it's pulmonary vascular remodeling, and it typically, again, affects the smaller vessels, and you just lose vessels. So what we do is tune our parameters, change the alpha and beta a little bit, so you get fewer vessels of any particular radius as you go through the system. And that's how we model rarefaction. And then chronic thromboembolic pulmonary hypertension is where you, as its name suggests, you get blood clots that then affect the behaviors of the small vessels. But typically, it manifests itself initially as increased stiffness and decreased cross-sectional area in the larger vessels. So we've modeled stiffness in the larger vessels, and we're going to compare the pressure pulse from these. Again, this is to help in clinical diagnosis. Here are cartoons showing the sort of effects that you get and the classical information that you would be given by clinicians. For example, with loss of vascular bed, you can see this increased pressure rise and changes in the timing of the pulses, and clinicians will be very keen to point out features such as this, which tell you something about the forward and reflected propagating waves. So you get waves reflected from bifurcations. So this is the effect of increasing small vessel stiffness, and we're increasing it by about 10% each time. This is in the main pulmonary artery, and then in the right superior vein at the bottom. These are pressures, these are flows, and flow, of course, is imposed here. And these are summary data, but I won't bother with those right now. So you can see peaking of the pulse and delays in the and earlier peaking of the pressure pulse in the veins, earlier peaking of the flows here as well. So these are characteristic features of that and consistent with what the clinicians see. By contrast, if you have small vessel stiffness, you see that the pressures don't peak and they tend to rise uniformly. So there's a very classic signature to this sort of disease. So this is useful for identifying what happens. And the thing that's useful for us is that we can go back and tweak parameters in our model to see what produces these features. So we can actually see cause and effect and do things that you wouldn't want to do or be allowed to do to patients or animals at all. So that's one of the features of the model. And in particular, we can look at what happens in the smaller vessels. So this is the healthy case, and this is the effect of increasing or reducing the vascular density. And you can see the very rapid rise in pressure and how it is transmitted through the system. So these are mean pressures. And we can look at the pulsatile flow as well. So you can relate that then to the sort of remodeling that will have to go on in the system to try and cope with that. You have to remember that all of these vessels are dynamic in some sense. And then this is stiffness in the large vessels. You see very different signatures here. You see the peak arriving earlier and uniform changes in pressure here and so on. So you can identify the different diseases, and particularly this early arrival of the pressure peak. So what else can you do with a model? Well, one of the things you can do is look at forward and backward travelling waves and understand what's happening in bifurcations, and this is called wave intensity analysis. It's not just something I'd want to do with a model. I guess over the last 5-10 years there's been quite a debate in the physiological community about this sort of analysis to understand what's happening both in the systemic and the pulmonary circulation. And so we can do this work in our model and again understand what's going on here. So I won't take you very much through the governing equations. It's the same governing equations. The main thing is that these equations are hyperbolic, and so you can cast them into a standard theory with Riemann invariance and with characteristic paths. C here is the wave speed and U is the fluid velocity, and this is fine provided friction losses are small, which is certainly okay in the larger vessels. And in particular, it depends on the pulse wave velocity, which we know exactly in our model because we know what we put in. And if you assume that at the end of diastole in the arteries that the flow is more or less steady, you've got a steady cross-sectional area, then you can work through your analysis looking at forward and backward travelling waves, defining them in a sensible way, and you can then write incremental changes in pressure in terms of the forward and backward Riemann invariance, and so you can identify the forward and backward waves by setting either the components in the components of the Riemann invariance to 0, according to whether you're going backwards or forwards. So these are our final expressions. You can integrate them up if you need to, and you define wave intensities in this way, and we're going to take incremental values with small time steps to calculate these things. In most wave theory, you'll know that wave intensity is defined in this way, but when you have a discrete sampling time, you want something that's independent of your time steps, so you divide by the increments in time, the time steps as well. This is a standard theory, and this is the discretized version of that. Now, one of the things that's of interest to the clinicians and something we can learn from our models is how do you estimate the pulse wave velocity? We know ours, but they don't. One of the things they do is to plot in, say, the aorta, a pressure, fluid velocity, blood velocity curve over one cycle. And what you'll see is at the beginning of the cycle, when this is in systole, when the left ventricle is contracting and blood flow is being ejected, you get an almost straight increase here, from which you can estimate dp by du, and you can estimate the pulse wave velocity. But that's not the only way of doing it. You can take a root mean square average, which they like to call the sum of squares estimate, for the pulse wave velocity. And so there are questions about, well, does this make any difference, and is it important? So here's simulated wave intensity analysis. This is actually for our pulmonary circulation, but the same thing holds true in terms of estimating the pulse wave velocity. And these show increments in pressure over the cycle, and you have compressive components of the waves here and decompression waves here, expansion waves if you like. And the key thing is that early on there's a reflective wave that is coming backwards from the first bifurcation, and that helps to lower the pressure for the right ventricle. So it lowers the load on the heart, is the way clinicians would see that. So that's a useful feature that we've evolved. And we find this too in our model. It wasn't built in deliberately. Oh, and these are just graphs showing time against space, and you can see the forward and backward waves propagating through the system. So we can do that. But what if you use different estimates for the pulse wave velocity? The key thing here, I'll just identify it here, this is if you use this root mean square, the sum of squares, you lose the feature that is this backward decompression wave. You actually get a compression wave, and you increase the pressure in the system because of that. And so this is a very poor estimate we find for what's going on in the system, and we really would advise against using it. This is okay, it produces many of the same features. So the last thing I'd like to tell you about is our most recent work, so this is actually under review at the moment, and this is coupling the left ventricle and systemic arteries, because what we want to begin to understand is what is the effect of coupling the ventricle to arteries, and indeed in the pulmonary circulation, arteries and veins. Now, why are we doing a left ventricle? Well, it's because we don't have a model for a right ventricle yet, though it, in principle, shouldn't be so hard to do. But you need to do both together because of the way the heart is structured. The right ventricle is almost tagged on to the left ventricle. So the cartoon illustrates what we do. So Xiaoyu Luo and Hao Gao and also other colleagues, Boyce Griffith in the States, who was a student once of Charlie Peskin's, have an immersed boundary finite element model for at least part of the left ventricle here, and then they put on outflow tracks. And this does proper 3D flow, it does proper soft tissue mechanics, and has a proper contraction in. So it's quite a sophisticated model. So it takes account of fiber directions. It has the best model we have for soft tissue mechanics, the one that Holtzapfel and Ogden have put together, and has proved to be quite successful. This one doesn't have valves in, but they're building models with valves in, and we're putting them into these circulation models. So how do we link the two things together? Well, this cartoon illustrates it. You've got outflow from the aorta in the heart linked to the left ventricle, and then you link it to our cross-sectional average, this 1D model, which is what the cartoon is supposed to illustrate. And what you do is match flows and pressures in a systematic way, and it works and converges very easily. It's not a sophisticated thing to do, really. You output a flow, put this into the arterial model, then back calculate the next pressure, feed that back as an average pressure to the heart, take another time step, and so on. And here's a cartoon of how well the model in red fits the MRI data. And the fit is pretty good. This is a cross-section, except perhaps in the apex, and what's missing in these models is a pericardium, which is a membrane that holds it all together. And that's something for future modeling. So there's a bit too much on here for you to read, but it's really for me to remind you that the two systems are only coupled when the aortic valve is open, because that's when flow is out. Once the pressure drops too low, you start to get backflow, the valve closes, and then the arteries model carries on. You get waves propagating backwards and forwards through the system, through diastole, and the heart then goes through a whole business of valves opening and closing and filling up. I can tell you more details about that if you're interested. And to illustrate the sorts of things that we can do, again, we can simulate disease, and we can look at what happens if you stiffen the arterial wall. I think this is stiffening of the smaller vessels. We can look at rarefaction of vascular beds. So this is not pulmonary hypertension. This is what happens in, for example, type 2 diabetes in the systemic circulation, and is one of the nasty complications of that. We can also look at having a stiffer LV, left ventricle, and also increased contractility. The myocytes are contracting more. Just to illustrate the sorts of things that we can do. And a common thing that clinicians would look at is to look at pressure against volume loops as the heart goes through a cycle, or the left ventricle goes through a cycle. And these are for various cases. Red is the baseline. This is the filling and repressurizing that goes on before the left ventricle pumps. This is the pressurization, and where the curve starts to go off, this is where the aortic valve opens, and then this is the end of diastole. Pressure is dropping, and then there's refilling going on. And of course, the area under these curves is a measure of work that's done. Stroke work is the clinical phrase, and stroke volume is the length of this curve, how much change in volume you're getting to pump blood out. And the sorts of information you can get are, you can see that stiffening the arterial wall, increasing the rarefaction of the vascular bed, increasing its resistance, and decreasing the compliance as well, all reduce stroke volume. In fact, decreasing the compliance has a marked effect on the overall work and circulation as well. And what's important for us is that compared with the systemic arteries model on its own, when you put a left ventricle model in, you find that pressures and flow rates decrease by up to 10 or 20%, which is actually quite a lot. It's a lot clinically because the heart itself can remodel. You know that athletes tend to have bigger, stronger hearts and slower heartbeats and so on, but they can remodel to cope with excess pressure and excess flow rates. So you can start to get clinical conditions where things go wrong in these cases. And so estimating these is quite important. This happens to show pressures and flow as they would be measured at a cuff. So mid-brachial refers to arms here. And again, you get corresponding results in the flow in the arteries illustrated by this. Again, red was the normal case. Black is the worst case where you've got a stiffer ventricle, and so on. So you can see these effects in pressure and in flow. You can also use this just to understand what you can and cannot measure with cuff pressure. So these are for the 4 cases again, and this is a normal case. This is illustrating the left ventricle pressure, so just inside the ventricle through systole, and then we've cut it off here. Then the pressure in the aorta as you go through systole into diastole, and you can see the increase in peak pressure under what would be a pressure cuff. And we can use this to investigate what happens in different diseases. The fact that there's a difference here doesn't really matter to clinicians. It's just what you use as your normal baseline. But again, for the various cases, we can see the pressure difference, and these are mean pressure difference or pressure differences in, again, millimeters of mercury, showing the sorts of things that you can detect and not detect. So it's useful for understanding clinical measurements. So I'll finish there. Amongst other things, we believe ours are the first simulations of pulsatile flow throughout the pulmonary circulation. Of course, there's more things to do, as always. With these models, we can calculate pressure and flow in the small vessels, and that provides the mechanical environment for multiscale interactions, understanding what's happening in soft tissue. We can investigate diseases of the small blood vessels, such as diabetes and pulmonary hypertension, and we now have a tool for exploring interactions between the heart and the circulatory system, the rest of the circulatory system. Of course, this isn't the end of the story. Our patients or people undergoing clinical investigations are normally lying on their backs under scanners, and we haven't done anything to model what happens when you exercise and so on, and that's a whole different problem. Indeed, even standing up is a different problem. I haven't done any work on this, but Mette Olofsson and colleagues have done work on the baroreflex, for example, which is what happens when you, well, they put them on a tilt table, but when you stand up, your whole system has to adapt very rapidly to control blood pressure and flow. And finally, well, what's the use of some of this? Well, there are many things. Understanding the basic system. Work that's currently going on is to do some patient-specific modeling for patients with pulmonary hypertension. They're subject to invasive and potentially dangerous pressure measurements, which involve putting a line in through a vein in the neck, an artery in the neck, and going through to the heart and through into the main pulmonary artery to understand what the pressure is. And this matters to clinicians because the different types of diseases have different causes and have different treatments. And though this is unfortunately a very serious disease, longevity has been improved over the years by understanding how to treat patients. And what we hope is that with the sort of data we can get from MRI scans that are done almost at the same time, within a couple of days, it's part of a whole cycle, we can, given one set of invasive pressure measurements, after that be able to make reasonable estimates from just MRI scans and understanding how cross-sectional areas vary as the pressure pulse goes through in the larger vessels, we may be able to take away the need for these repeated invasive pressure measurements. So that's, I think, a realistic goal. And we're also doing that with one of our professors of statistics, Doug Hoosmaier at Glasgow, who's an expert in estimating in a sensible, proper statistical way parameters in PDE models like this from data. So you're fitting curves and doing the whole thing properly. So that's one of the aspects that we're working on in the future. And then finally, a shameless plug is that we have got an EPSRC Centre for Mathematical Sciences in Healthcare. Mark Chaplin is one of the investigators, along with several of us at Glasgow. And we are about to advertise a number of postdoc positions and also PhD studentships. Postdoc positions to start from April onwards and PhD positions for next year. So if you do have good candidates or know of them, please refer them to us. We're very grateful for that. Okay, thank you.
Any questions for Nick?
I have two questions. The first is, the first part of your talk, you had very impressive data matching your model predictions. And I was wondering, how many free parameters did you have? Was there some type of fitting for that, or did this surprisingly emerge by putting in?
So we estimated as best we could the parameters for the vascular beds. So you did that a priori. You didn't tune it in any way. The parameters that we did measure were the ones I referred to, like the geometries for the larger vessels, which are specific to individuals. And of course there was a measurement of the cardiac outflow from the left ventricle. But that was it. We didn't fit anything else. There is one parameter in there actually, which is the external pressure on the large vessels, and that the effect of that really is more or less just to raise or lower the pressure. And I guess we don't understand it fully, but it's to do with the pressure of the surrounding tissues. So these vessels, you can excise them and make all these measurements, but when they're really surrounded by tissue, and so that has some effect on that. So that's the one parameter.
So my second question then is following on that. So the geometry is really critical for those.
Yes, because if you've got waves going backwards and forwards, the length of vessels and also the changes in area are quite important to the reflection coefficients.
So would you be able to extrapolate and, for example, deduce what those curves would be for a child or for someone who has like a very different geometry? Because that must be a totally different
So
scale.
I haven't looked at any physiology for a child.
7-year-old, I don't know, whatever.
Yeah, but we just don't have data for that. There are, of course, problems that children have, but pulmonary hypertension is not normally one of these. So you just don't have access to that
But what
sort
does your
of
model
data.
predict?
So we haven't done it for children. For adults, yes, because we are now collecting patient-specific data, and you will get changes due to that. I think most of the things that we are expecting to look at are changes in stiffness rather than changes in the geometry of the very largest vessels, though that may occur when you've got very high pressures, and we'll have to get more data before we can comment on that further.
Thank you.
The one sort of detail that concerns me in particular, you showed us some data on the lengths and diameters of pulmonary arteries, and apart from the main one, they're all pretty short compared with their diameter. So the idea of thinking, I mean, the whole early part of your modelling on the wave, well, all of it, I suppose, on the wave propagation, is based on the one-dimensional assumption, which actually includes the assumption that the lengths are large compared with
amplitude.
And all that. And so, how accurate? I mean, it's obviously working very nicely, and I'm not criticising the results, but I want to know how important it is that actually, if you're looking at the fluid dynamics anyway, it's not very one-dimensional anywhere. in the pulmonary arteries or veins, I suppose.
So I think that, well, there are two things in there, aren't there? Well, one is whether the amplitude to length ratios are okay, and I agree with you, some of these vessels are quite short. We haven't seen problems with that. I'm hoping that from the measurements we're going to get from the clinicians, we get pressures and flows, and we can go a little bit further down the system and just see how realistic those are. And that's what I think
the
tested.
reflection coefficients and things at
Yes.
each junction does assume that the junction occupies zero
Yes. Length, maybe?
dimension
Yes.
compared with the length of the tube and, of course, the wavelength of the wave, which is very much longer than anything else.
Yeah, I think you're right, Tim. And what I'm hoping is that the data we're beginning to collect now is going to be able to give us some answers to those sorts of things, because we're going to get more detailed pressure measurements further down the system. And that will enable us to know more, and hopefully one or two flow measurements down there. And then we'll be able to really compare that and see if there's a problem or not. I think the three-dimensionality is of the flow is probably not a major problem. I think initially when Meta did her work, she was perhaps concerned about pressure losses, particularly in the aortic arch. But in the rest of the system, it's probably not a great source of pressure losses. And in fact, we don't bother with that term.
So your linear resistance term, which is a gross simplification, doesn't matter because it's not very big.
Yes. Yeah.
I don't know. I mean, you say you haven't really looked into it much further, and probably, I'm fairly familiar with meta stuff. Probably nobody has. But I wonder if you have any thoughts about the breathing cycle. You know, because you're looking at pulmonary circulation.
Yes.
Your vessels are in parallel with the airways.
Yes.
And in the inhalation, you've got an expansion of the bronchioles and so on. You've got some massaging of the capillaries by the dramatically expanding alveoli. And I wonder if you have any thoughts as to what's going to get modified severely if you're when you're looking at the breathing cycle.
I think well, first of all, what's done in the MRI scanner is that patients are asked to hold their breath. This is because you need to try and keep the geometry fairly fixed. So we know what we're comparing against. So it's legitimate in that sense. I think if you're lying down and breathing shallowly, I suspect that this is a slow variation on what you're already seeing. When you're exercising, I don't know. I think I wouldn't claim that if you're running hard and heart rate is up high, and pressures are up high, that this model would be good. In fact, I think you need to look carefully at the tube law at those pressures as well. So there are lots of things there to be looked at. What things are we working on between as well? We're looking at better modelling of the tube law for these more extreme cases. Viscoelasticity is thought to be important to some extent in the data here. It's also true that for healthy individuals, the heart rate is not completely constant. There's a variation in heart rate, there's a variation in stroke volume, which is just normal. Even in healthy individuals, your heart can occasionally more or less miss a beat, and you don't notice it, but you can see it on the tracers. So the assumption that it's periodic is an approximation, though I think you can do something using Laplace transform methods rather than Fourier transform methods. So there are lots of things to be looked at there. I think in terms of the way the lungs work, the other big thing is that we're looking at patients lying down. As soon as you stand up, there are tidal effects, the changes in pressure just because of gravity, and also in the way the circulation goes through the lungs. So right now, probably only a third of my lungs are doing much work in terms of air going through and blood flow, major blood flow through. But if I was exercising fully, then presumably they would all be working. So there's a lot of reservoir capacity there as well. So tidal effects are probably quite important. That's something we could put into the model. And I think clinically it gets referred to as various zones and so on. The other thing we really want to do is to model flow around the alveoli. We have some ideas, but nothing completed yet.
Okay, I think that's a nice place to stop. Perfect time for coffee. So just remains to thank Nick once again for a very nice talk.
Thank you.